Hello, my dear students. Welcome back to one more lecture on advanced econometrics. In our previous lecture, we were discussing about uh, dynamic econometric model. So in that video, we have discussed what is the nature of a dynamic model and why we need to include a lagged variable in many econometric models, especially in macroeconomics and finance. Okay, yes. So in this video, what we are going to discuss is how we can estimate a dynamic econometric model. So the estimation technique that we have uh, that is very popular is the OLS method. Okay, but in order to apply this OLS method, we need to satisfy certain assumptions. But when we have a lagged variable in our models, many of these assumptions may not be satisfied, or some of the assumptions may not be satisfied. So OLS is not a right choice when we have a lagged variable in our econometric model. Okay, so there are large number of different methods that are available. Okay, so we will look into what are these methods. Okay, so a model which include a lagged variables can be either the distributed lag model or it may be an autoregressive model. Both are dynamic models, but they are different in terms of which lagged variable we are including. Whether we are including the lagged values of your explanatory variable, then it will be a dynamic or distributed lag model, or if you are including the lagged values of your dependent variable, then it will be autoregressive models. Okay, both are different. Okay, so first we will try to explore some of the techniques which is available for estimating this distributed lag models. Okay, and the first method is the OLS method. Okay, or a revised model of OLS method, or what we called ad hoc OLS procedure. Okay, so it is not basically OLS but a what we call a reduced form of OLS. Okay, it is called ad hoc OLS. Okay, and second, first we will discuss what is this OLS model and how we can uh, estimate the distributed lag model using ad hoc OLS procedure. Okay, second, what we do is we will the second method is the Koyck method. Koyck is the name of an econometrician. Okay, so he has devised a method, and this method is named as Koyck model of distributed lag models. Okay, and for this Koyck model, uh, there are certain problem with this Koyck model. The most important problem with this Koyck model is it is a purely algebraic model, or this model is derived using certain mathematical techniques and which is not based on any economic theories. Okay, so there are two rationalization of this Koyck model, or two different persons or two different models rationalized this Koyck model or Koyck procedure by giving certain uh, economic theory or theoretical base. Okay, so such two models are adaptive expectation model and partial adjustment model. These are all not two different methods, but a method that rationalizing the Koyck procedure. Koyck procedure. Okay, and one more method is there, Shirley-Ahlmann's polynomial distributed lag model, or Ahlmann's approach. Okay, so this method overcomes certain limitations, certain assumptions. The Koyck model is based on certain assumptions. Okay, so many times this assumption is not valid. Okay, so in such time, uh, in order to overcome such problems, the Shirley Ullman developed a model called the Ullman polynomial model. Okay, so there are mainly 5 different approaches are available to measure, to estimate the distributed lag model. First one is ad hoc OLS, second one is Koyck, third and fourth are not two different model, but taking the procedure of Koyck and applying into certain two theoretical base or two separate theoretical idea, this Koyck procedure is applying. Okay, so it is called rationalization of Koyck models. The first one is the adaptive expectation model, and the second one is the partial adjustment model. Okay, and in order to measure or estimate this autoregressive model, only one technique is available. That technique name is called the instrumental variable method, or it is known as IV method. IV means I stand for instrumental, V stand for instrumental variable. So IV method is instrumental variable method. Okay, yes. And third type of, if you look at this here, it is not an estimation technique, but it is a method to check the causality. Okay, so causality is mainly analyzed using certain past values. Okay, so a method is available to estimate or to check which variable is leading to which variables using that variable's past values. Okay, so there are such kind of analysis there. For that we are using Granger causality test. Okay, so this Granger causality test is not a test to estimate the parameter, but to estimate but to check whether two variables are, whether they are leading to one variable is leading to other variable, or the other variable is leading to this variable. For example, if GDP and money supply is the two variable, whether this money supply, whether an increase in money supply will lead to an increase in GDP, or an increase in GDP will lead to money supply. Okay, so if we want to check such kind of causality, then one method is available. It's called the Granger causality test. Okay, yes. So basically, in order to estimate the distributed lag model, 5 methods are available. For estimating the autoregressive model, only one method is available. Okay, and for checking causality, one more method is there. It is called the Granger causality test. Okay, now first we will look into this ad hoc OLS procedure. Okay, then we will come to Koyck model. So in this classes we will discuss two methods, ad hoc method and Koyck method. So in order to explain you the ad hoc procedure, let me take an infinite distributed lag model. Infinite means what? We don't know exactly how much lag should be included. So what we are doing, we are taking n number of explanatory variable or n number of lagged values. Okay, so this equation is yt is equal to alpha plus beta 0 xt plus beta 1 xt minus 1, beta 2 xt minus 2, beta 3 xt minus 3, then beta k xt minus k plus ut. Okay, this is what is called infinite lagged or infinite distributed lag model. Okay, so here we have 3 different types of parameters, as I told you before: short run parameter, intermediate parameter, as well as long run parameter. Okay, yes. So this Alt and Timbergen, two econometricians, suggested an alternative method to estimate this equation. Okay, and their procedure is known as ad hoc procedure to OLS. Okay, so what they have done is, or what they have suggested is, do OLS sequentially and stop you stop your OLS procedure when the regression coefficient of lagged variables start becoming statistically insignificant, or at least one of the variables start becoming uh, changing its sign. What is this? It means that suppose we have a variable yt and xt. Okay, what is mean by OLS, doing OLS, or uh, doing OLS sequentially means what? First you do a regression on yt on xt. That's the first regression. Second, do a regression of yt on xt minus 1. We are included one lagged values. You look at whether this t minus 1 or the lagged variable's coefficient is significant or not. It is significant, okay, no problems. Then again what you have to do, yt on xt, xt minus 1, xt minus 2. We are included one more lagged values. Now you check the significance level of the variable that you have included. We have additionally included yt minus 1. So you look at its coefficient, whether it is significant or not. It is significant. Now you include one more variable xt minus 3, but now it is not significant. So you stop there. Where you have to stop? xt, xt minus 1, xt minus 2. Don't take xt minus 3. Okay, or xt minus, the coefficient of this xt minus 3 is significant, but xt minus 1 coefficient, xt minus 2 coefficient, both were positive, but when we included xt minus 3, its coefficient is becoming negative. There also you have to stop. Okay, so its steps is regress y on xt, regress y on xt and xt minus 1, regress y on xt, xt minus 1, xt minus 2, and so on, and stop when one variable becoming statistically insignificant or its parameters change its sign. Okay, so this is what is called as ad hoc OLS procedure. So let me check how we can do the ad hoc OLS procedure. Okay, yes. So look at this data. Okay, this is the variable yt. This times this variable, so it is starting from 1970 to 1999. Almost 20 years of data is there. This is y and this is x. Okay, now what is meant by xt minus 1? Here you don't have xt minus 1 because xt past values are not available. For this 1, 2, 8, 2, 3, its past value is nil, because if you look at the data beyond, or if you look at the data 97, 69, it is not available. Okay, so this data is not available. But if you look at 13218, its past value is 128 xt 12823. Okay, so xt minus 1 is equal to, this is the data. Okay, yes. So for this data, for this value, just previous value 1328. Okay, for this, okay. So here when we take xt minus 1, one value will not be available in the first, and if you take 2, 2 values are not available. If you take 3, 3 values will not be available, and if you take 4, 4 values will not be available. This is the way how we can construct the lagged values. Okay, now what you have to do is, let me select this data. Okay, yes. Okay, now what I have to do is, I am going to check data, data analysis, regression, Y range. This is our Y range. Okay, and what I have to do is, I'm just checking, only taking only one X only. Label is not there. Yeah, yes, you check it. The intercept is 1 minus 1778, and the variables X, its coefficient is 0.99. Okay, so that first step is over. I am going to repeat this. I am going to add one more explanatory variable, regression. Okay, okay. So this is my second. I am starting from here. Okay, Y, then I am taking xt, then xt minus 1. I have included one more lagged values. Okay, check it. Okay, now you check it. The first variable's symbol is 1.1, but when you take the lagged value, it is negatives. Okay, and this was significant and this is not significant. Okay, so here itself we can say that the first lagged values are not significant. Okay, so it means that your lagged values will not have any impact on your dependent variables. Okay, we can continue adding one more variable. Okay, go to data, regression. Okay, so here I am taking these values. Okay, then X is, I am taking, oh sorry, yeah, okay. This is Y. Yeah, this is X dimensions. Okay, now you check it. Here also these two p-values are not significant, and when you take one more, when you include one more explanatory variable or one more lagged values, the simple or the coefficient is becoming the positive coefficient becoming negatives. Okay, and it tells us that the coefficients is not significant as indicated by p-value and t-value. Moreover, if you include more and more lagged values, the coefficient is becoming coefficient is changing its sign. Positives are becoming negatives. Okay, so it means that here the negative as per this ad hoc estimation, there is no need to include the lagged values because lagged values is not showing any significant impact on your dependent variable. Okay, yes. Now There are certain problems with this ad hoc procedure. The first problem is how much lags we should include. Actually, here we don't have a proper method to tell you this much lag should be included. Okay, what we are doing is we are running a trial and error method. If you include one more variable, check it. If it is not okay, remove it. Okay, so it is a time consuming process. Okay, and we don't have a prior restrictions or prior information to determine how much lag should be included. This is one of the most important problem with this uh, ad hoc estimation procedure. Second problem is, as we estimate or as we include successive lags, okay, the degrees of freedom, we are losing the degrees of freedom. And when we use a lagged values, we are removing the first observation. When you take first lag, you remove the first observation. Second lag, two observation. Fourth lag, you have to remove first four observations. It means that your degrees of freedom will be lost. Okay, and it will make the statistical inference problematic. And third one is, if you include the successive lags xt minus 1, xt minus 2, xt minus 3, okay, xt minus 1, xt minus 2 and xt minus 3, all this will be highly correlated, which leads to the problem of multicollinearity. What's the multicollinearity problem? Linear high correlation between one or two or more independent variable in your multiple regression model. Okay, so this is a multiple regression. In this, we are including many lags, and these lags may be correlated with each other, and this will make the problem of multicollinearity. Okay, yes. So what we do? So Euler's is not a right choice. Euler's is not a good choice because it has many problems. Okay, so in order to overcome the problem associated with this ad hoc procedure, many alternative model has been suggested by various econometricians. Okay, and we will look into what are all these alternatives. Okay, the first and most important theoretical model is the Koyck model. Okay, but Koyck proposed a pure algebraic model or pure mathematical model to estimate a dynamic econometric model or distributed lag model. Okay, so you have to remember the thing is that the Koyck model is basically a mathematical model, or he has achieved or he has developed this model only through a mathematical technique. Okay, yes, we will see how he has developed his models. Okay, so here also you assume an infinite lag distributed model like yt, I have alpha plus beta 0 xt, beta 1 xt minus 1, beta 2 xt minus 2, beta 3 xt minus 3, up to beta k xt minus k or xt minus un plus ut. Okay, then as I told you before, in this model, beta 0 will be the immediate impact. Okay, beta 0, beta 1, beta 2 will give us intermediate impact, and sum of these betas, beta 0 plus beta 1 plus beta 2 up to beta k will give us long run parameters. Okay, now Koyck, he has assumed an important thing, or this Koyck procedure is basically based on one assumption. Okay, the assumption is all these beta i's will have the same sign. That means if xt simple is negative, or the parameter of xt is negative, so this beta 0 is negative, then beta 1, beta 2, beta 3 up to beta k will be negative. If beta 0 is positive, the remaining betas will be positive. Okay, yes. And one more assumption he has made is, he assumed a geometric probability distributions, okay, and he also assumed that all betas will decline, or the beta will decline geometrically, okay, as if beta 1 is lambda into beta 0. Beta 0 is what? Immediate impact. Okay, so if beta 0 is if beta 0 is a value, beta 0 into lambda will give you beta 1. So what is beta 2? Beta 2 will be lambda square into beta 0. Beta 3, lambda cube into beta 0. Then what will be the beta k? Lambda k into beta 0. What is beta 0? Initial impact. Okay, so we are multiplying initial impact with a value, and this value is indicated by lambda, and this lambda value will be all this successive parameter will be declined geometrically. This is the assumption which is made by this Koyck. Okay, so this lambda will be rate of decline or rate of decay, or yeah, we can call it as a rate of decline. And this rate of decline will always lies in between 0 to 1. Okay, yes. So if it is if lambda is rate of decline, then what will be the 1 minus lambda? Going back, speed of adjustment parameter. Okay, so if lambda is equal to, if lambda is the rate of decline, then 1 minus lambda will be the speed of adjustment. Okay, and as the assumption says that each successive beta coefficient is numerically less than each preceding beta, implying that as one goes back into distant past, the effect of that lag on yt become progressively smaller and smaller. Okay, what does it mean? We know that the contemporaneous effect will be more than that of the lagged effect. Okay, and that means, suppose as we going distance to past, the effects of a variable or effects of an event on a particular variable will be decreased. For example, if suppose today, suppose if the American election, assume that today is American election. Okay, so this is one of the most important event in the world. American election is one of the most important election in the world, which will have an impact on each and every financial market. It will impact overall financial markets. Okay, so today was the election. The Trump has came in again into power, assume. Okay, so it will have an impact on today's stock market. Okay, tomorrow also it may impact, but day after tomorrow the impact will be less and less. The impact will be there, but it will be less. Then it's after day the impact becomes 0. Okay, so as we move to distant past, the impact will be progressively smaller and smaller. Okay, so impact of xt minus 1 on yt will be greater than that of the impact of xt minus 2 on yt. Okay, yes. Now, as I told you, the lambda is in between 0 and minus 1. Okay, and if it is close to 1, the rate of decline will be slow. Okay, and if lambda is close to 0, then higher will be the rate of decline. Okay, now by assuming three different things, that is, the lambda will be non-negative, okay, all beta I should have the same sign, and each successive beta coefficient is numerically less than that of the each preceding betas. Okay, so by assuming all these things, okay, what will be they have derived the sum of the betas or the long run coefficient. Sum of the beta k means what? Beta 0, beta 1, beta 2, beta 3, beta 4, beta 5 up to beta k, the sigma beta k. Okay, so this will be equal to your immediate effect, that is beta 0 plus lambdas. For first value, lambda is not there. Okay, if you look at here, look at here, 1 lambda, lambda square, lambda cube, lambda raised to 4 up to lambda raised to k. Okay, so similarly, if you take the sum of the beta, it should be beta 0 multiply 1 plus lambda square plus lambda cube plus lambda raised to 4 plus lambda raised to 5 up to lambda raised to k. This is what? Sum of the geometric progression. Okay, or sum of the infinite geometric progressions. So you might have learned in your schoolings the basic mathematics. What is the sum of an infinite geometric progressions? It will be the initial value multiplied by 1 divided by 1 minus lambda. Okay, so here it will be beta 0 into 1 divided by 1 minus lambda. Okay, this is basically the sum of the geometric progression of an infinite series. Okay, yes. So this value will give you a long run multiplier. Okay, so as a result of this, so we can rewrite our infinite equation as yt is equal to alpha plus beta 0 xt plus beta 0 lambda xt minus 1 beta 0 lambda square xt minus 2 up to ut, up to last value plus ut. Okay, so here what we have done, by making some assumptions, okay, we have converted our initial infinite Laggard equations into another equations. Here we are including not only the coefficients, or we are multiplying the coefficient with the rate of decay or rate of decline. Okay, yes. But the question is, can we apply Euler's here? We cannot apply Euler's here, because if you look at the equation, here one parameter is multiplied with another parameter. Beta 0 is multiplied with lambda. Here beta 0 and lambda square, it violates one of the fundamental and most first assumption of Euler, that linearity in parameter. This assumption is violated. Okay, so we cannot apply Euler's into these equations. Okay, so what Koyck has done is, Koyck was a very tricky fellow. He want to make it Euler's to be applied, or he want to apply Euler's into these equations. For that, what he has done, he, by making some mathematical manipulation, he has converted this nonlinear equation into a linear equation, and this procedure is known as Koyck procedure. Okay, so we will see how he has changed this models. So what will be our original model? This is our original model. Yt is equal to alpha 0 plus alpha plus beta 0 xt, beta 1 xt minus 2, beta 2 xt minus 2 up to beta k xt minus k. Then what is the last model, or the Koyck transformation, or the Koyck transformed the original model using the rate of decay. So what is that equation? Yt is equal to alpha plus beta 0 xt plus beta 0 lambda xt minus 1, beta 0 lambda square xt minus 2 plus beta 0 lambda cube xt minus 3, which will go like that up to k plus ut. Now you take one period lag of this model. So this is the model. You take one period lag. So yt become yt minus 1, xt become xt minus 1, xt minus 1 become xt minus 2, xt minus 2 become xt minus 3, ut will become ut minus 1. This is what is called the one period lag of this model. One period lag. Okay. Now this one period lagged model you have to multiply with lambda. What we are doing here, we are multiplying the entire thing with a constant values. Okay, you look at this, yt minus 1 into lambda yt minus 1, alpha into lambda plus beta 0 lambda xt minus 1, beta 0 lambda is there. So lambda multiplied by lambda square. Here lambda square is already there, lambda into lambda square, lambda cube. Okay, and last one is ut minus 1 multiplied by lambda ut minus 1. Okay, now what you have to do is you subtract this equation from this equation, yt minus lambda yt minus. What is this yt? Yt is basically this equation. This is the yt equation. This is the lambda yt minus 1 equation. You subtract this equation from this equation. Okay, if you look at these equations, you can see that this if you look at this is cancelled and this is cancelled, this is cancelled, this is cancelled. Okay, suppose if one more term is there, it will be beta 0 lambda cube xt minus 1. Okay, so all these terms are cancelled out, and the only remaining thing is this is the remaining things. Okay, then one ut is remaining here, then here, yeah, lambda into alpha is remaining there, then this also remaining there. Okay, yes, now what you will get, if you do it, then it will be yt minus lambda yt minus 1 into alpha into 1 minus lambda beta 0 xt plus ut minus lambda ut minus 1. If you rearrange it, or that means this is, if you bring this into right hand side, okay, what you will get, yt is equal to alpha into 1 minus lambda beta 0 xt lambda yt minus 1, minus will be plus, so lambda yt minus 1 plus vt. This vt is nothing but all these terms. Okay, so now if you look at the equation, it is linear or non-linear. Is it linear? Because non-linear parameters has been gone from these equations. Okay, so what he has done is he has converted a non-linear model into a linear model, using some mathematical techniques. By taking one period lag, by multiplying a lambda, and by subtracting, he has derived a linear model. So this is what is called the Koyck transformed equations. Koyck transformed equation. Okay, yes. Now we have started with a large equation, xt minus 1, beta 0, beta 1, beta 2 up to beta k. But now you look at this equation, it has yt, then one parameter here, one parameter here, xt and yt minus 1. Here we are having only 3 parameters to estimate. Okay, so we have started with an infinite lagged model. Now we have end up with a one lagged value. Okay, here we are having only one lagged here value. Okay, so this is the short term impact is given by this beta 0. Okay, and long run impact is given by this beta 0 into 1 divided by 1 minus lambda. Okay, then how you can find out the lambda value? From this you can find out this lambda value. Okay, and since lambda will lies between 0 and 1, the long run impact will be always greater than that of the short run impact. Okay, yes. Now the features of the Koyck model. As I told you, we have started with an infinite lagged model but end with a 3 variable model. Second one, we started with a distributed lag model but end up with a autoregressive model. That is very important feature of this Koyck model. We have begin with a infinite distributed lag model, but we have end up with a 3 variable autoregressive model. Okay, then if we want to find out the 50% of the lag, 50% of the long run impact, then it will be log 2 divided by log lambda, and the average lag length can be found out using lambda divided by 1 minus lambda. Okay, so these are some of the features of this Koyck model. Now we will go to the how to estimate the Koyck model using real example. Okay, I will show you that how to do that. Yes, so look at an example. Okay, the same example that we have used for ad hoc estimation. This is our y, this is our x. Okay, so you look at the equation, what we need. Okay, here yt is there, xt is there, and we have to construct yt minus 1. We have to construct yt minus 1. Okay, so here I have constructed a yt minus 1. You look at this. Okay, so for this value, yt minus 1 will be its just previous value, 11300. Okay, yes. Now go to data, analysis, regression. This is your y variable. Okay, and this is your x variable. Label is not there. Click OK. Okay, now we have got the result. Okay, so what is this intercept? Intercept is this is intercept. Okay, so what is, you look at the intercept. Intercept is basically alpha into 1 minus lambda. Okay, so this is not the alpha but alpha into 1 minus lambda, alpha 1 minus lambda. Okay, now the second thing is, yeah, this is xt beta 0. So this is the beta 0. Beta 0 is equal to this one. Okay. And third variable parameter, if you look at the third variable parameter, it is lambda. So, okay. So the lambda is equal to 0.410. Okay, so this is what is called rate of decline. So rate of decline is 0.41. Okay, now yes, so what will be the speed of adjustment then? Speed of adjustment is equal to 1 minus lambda, 0.589 something. Okay, this is the speed of adjustment. So short run impact is 0.63. What does it mean? In the short run, or immediately, if something happened to x, okay, y will be changed by 0.6. That means 1% change in x will lead to 0.6% change in y. Okay, then how we can calculate the long run impact? This is a short run parameter, beta 0 short run parameter. Then long run parameter is nothing but your beta 0 multiplied by 1 divided by 1 minus lambda. Okay, yes, n into 1.02. This is what is called the long run parameter. Okay, so if you look at this long run, this is long run parameter and this is the short run parameter. If you look at the long run and short run, long run parameter will be always higher than that of the short run parameter. Okay, so this is the way how we can estimate this Koyck model using example. Okay, so by simply taking some data, we can find out, we can estimate this Koyck model, we can find out the rate of decline, we can find out this speed of adjustment, and we can also find out short run as well as long run parameters. Okay, but this Koyck model is also not free from limitations. It has mainly two limitations. First one, it is very restrictive in its assumptions. Okay, so it assumes that all beta I have the same sign and that decline geometrically. Okay, so it may not be happen. Sometime beta may have the different sign. Some lagged values, coefficient may be positive and some are negatives. Okay, and sometime it may increase and decrease. So there may be a both increase and decrease, or it always may not be decline in a geometric progression. Okay, and second thing is it is purely algebraic, not theoretical. Okay, so if you look at this Koyck transformation from an infinite nonlinear model into a linear finite models, it is purely an algebraic models. He has rearranged each and every equations. Okay, and anyway he has finally derived a model. That's all. Okay, so this is all about this Koyck model, and in the next session I'll be discussing how this Koyck models, how we can incorporate the theoretical argument into this Koyck model. Okay, yes, thank you.